Amy Wu, who is here from the EPFL in Switzerland. And I will let Amy introduce her talk.
Can you hear me? Yeah? Okay, cool. Okay, so this talk is about some preliminary thinking about the effects of trunking on when we walk up slopes or when we walk faster. So this question came out of why do humans change our trunk angle when we want to increase speed or walk uphill? And so some of the previous studies have shown that perhaps this is to aid in forward propulsion by moving your body center of mass closer to the front and over your base of support to help you move forward faster. And some example could be, for example, with subjects with a spinal cord injury, they have reduced push-off as measured from muscle activity, but they have 1.5 times more lean forward. So when you think of trying to move your center of mass forward, there's a couple ways you can do this. You can simply move your trunk forward. You can also sort of, and keeping the angle between your legs symmetric, or you can kind of shift your body forward and then keep your trunk upright. Or you can do a combination of these things. So one of the things, our hypothesis is that when you move your trunk angle or walk up slopes, that this actually induces a change in the symmetry between your two legs. So if you look at just walking, you have alpha and, oh, yeah, there it is. It's gone. So you have alpha and beta, so these two angles are equal when you're walking normally. And then if you were to lean your trunk forward, one of the angles will be greater than the other. If you lean your trunk backwards, also there'll be a change. And then if you're going up slopes or down slopes. And so what we wanted to know is what are the different influences of the effects of when you change your trunk angle, when you change your speeds, and when you walk at different slopes. And we're defining asymmetry in this case as a difference in the angles between these two legs. So what we did was we did a study with 5 subjects. So we had them walk at 4 different trunk angles, 0, 15, 30, and at self-selected. They also walked at different speeds, a range of normal walking speeds, and up different inclinations. And so they did a combination of these parameters. So it's about 36 trials, and we wanted to know how this affects the asymmetry between their legs. And then sort of the side study also, we were trying to compare these results with this 3LP lean inverted pendulum model that my colleague developed, which I will actually explain more about for him in the afternoon session. So we take a look at the results. So if we look at how speed, trunk angle, and inclination varies with asymmetry, you see this increase in asymmetry as you would walk faster. So the angle between your legs would be more biased as you walk faster. And then, not surprising, if you were to walk up slopes, you also would have a big change in that. But if you were to move your trunk, actually the asymmetry between your legs would change. It would actually decrease instead of increase. And if you were to look at the model results, the model actually predicts this trend in a sense. It kind of overestimates the amount of asymmetry and kind of thinks there's going to be a big, sharp decrease with the trunk. But it kind of predicts it relatively well. So from looking at this and seeing that there's an increase in asymmetry with speed and with inclination, but a decrease with trunk angle, perhaps there's some sort of trade-off. And I'm not quite sure what the trade-off could be, but supposedly maybe between some sort of comfort and control. So what I mean by that is perhaps that when you increase asymmetry, but you don't lean your trunk in a certain way, this is actually very uncomfortable. So what I mean by that is this is a plot of the commanded trunk angle. So they had to put their trunks at different angles and what we measured. And if you take a closer look at when we command people to be 0, and look at the changes in slopes, so when we had to walk at steeper and steeper slopes, at 0 and 4 degrees, they're doing okay, and then at 8, they're kind of starting to cheat a little bit. There's a lot more variability in this. So it's getting harder for them, we think, to maintain this 0-degree trunk angle when they're at a steeper slope. And this is the self-selected angle, so where they really want to be at. So I guess I kind of call this the okay, ouch principle. So if you lean forward, it's okay, but leaning backwards, it's not really comfortable and perhaps is uncomfortable. Our 3LP model, which I will talk more about later, there's actually no sense of comfort in this model. It's purely mechanical based, but still you would see the same asymmetry come out of this model. So there's more to this story, so that perhaps there's a mechanical advantage for moving, having the asymmetry between the legs. And sort of on a related note, so looking at this neuromuscular model from Song and Geyer, when they optimize the reflex parameters to have the model walk at faster and faster speeds, the trunk actually moves further and further forward. So maybe there's some energetic benefit to also moving your trunk forward and between the asymmetry between your legs. So I'm going to take a quick commercial break. So if people here the last 2 years, you recognize the DARPA challenge, which is building low-cost robots that are stable but can fall. And apologies to the program managers. Matt, Peter, and I were didn't get a chance to organize it this year, but I want to give a quick commercial break update. So this is the robot from last year. So it's 2 legs that walk over ground, and it's powered. Low cost meaning under $50. And I just wanted to showcase 2 of my student projects. So this one is taking one of the legs away, so it's trying to deal with lateral stability right here. And then the other one is just trying to hop. So hoping building a slip-like version of the model to get it to run instead of walk. So yeah, to summarize, so we think trunk angle and inclination has a strong influence on the symmetry between the legs. There are advantages to moving your trunk forward to help you walk faster up slopes, but then you may have to compensate with your trunk angle to prevent a hip overextension as you move forward. So, thank you.
We have a question here. Julia?
How did you enforce the trunk angle during the commanded times?
Yeah, sorry, I didn't mention that. They have an IMU on their back, and they have a screen in front of them. So they have a target line and then visual feedback of what their trunk angle is, and they're supposed to maintain their angle roughly oscillating about that line.
In the way back there.
Polygon of support or ZMP measures for this? I mean, it seems like if you're on an upward slope, you need to lean forward so you don't tumble down the slope. So how does that sort of geometry play into these results?
Yeah, so we didn't look into those kind of things yet, but I think geometry would play a big role. And then I think that's one of the things as we compare this human studies with the linear inverted pendulum model, then there's different ways we can tease out what's going on there. But I think there's a lot of things going on here, so we're still trying to manage the thinking behind what it's related to mechanics or energetics and what is just kind of a consequence of moving up.
Yep, back there. Yep.
Yeah, sorry if I missed this earlier, but all these parameters seem to be time dependent. So how did you define, say, like leg angle and trunk angle?
How do we find leg angle and?
Yeah, is this measured at touchdown? Is this some sort of temporal average?
Oh, yeah, at double support. So yeah, so we found that leg angle at double support, and then because we had them walk at a combination of these different things, then we teased out what the contributions from these different parameters. So the plots I showed you there was the effect of changing one parameter over, say, its trunk angle over normal speed, but when we did our timing the contributions, we did actually a matrix of different, of these 3 different parameters.
Liz?
So for your definition of trunk angle, was that relative to global vertical or normal of the inclined plane or relative to the body?
So that was relative to vertical there. So we
So
had,
you don't take into account the inclination, so now they're going to be walking at an incline.
Yeah, so we re-zeroed it, and then we had them, it's relative to the flat, and then it's relative to ground. And then so we re-zeroed it, and then when we inclined it, then they had to do it relative to the ground. Yep.
Do John here?
I noticed that it seemed there was a 4-degree difference between the actual slope and the slopes preferred going uphill in one of your initial experiments. Did you find that to correlate, and was there a similar correlation for going down?
Yeah, it's a good question. We didn't study downhill, but I think it'd be interesting because when you go downhill, you do want to lean your trunk back. So I think there's going to be a slight difference and the behavior that will come out. So I think forward, it's really easy to lean your trunk forward, but I think backwards will be a little bit of a different a trend there because of that.
We have a question from the Slack channel.
8, Travis. Could trunk lean be used to keep muscles operating in safe and or economical regions on FL or FV curves, or even to operate muscles at velocity for peak power output?
Sorry, can you repeat?
Yes, sir. Is this better? Could trunk lean be used to keep muscles operating in safe and or economical regions on FL or FV curves, or even to operate muscles at velocity for peak power output?
Could be. I mean, your trunk is something you have control over, so you could use it to help you balance, maybe with angular momentum. So I think there's a lot of ways you can use your trunk in order to help and maybe reduce energetics.
I think Jonathan.
How can you speculate, because this is a question not on your study, but how might an ostrich or a guinea fowl or a bird that doesn't have a large upright trunk do this same thing?
Yeah. So when they lean their trunk forward, their legs could still be biased backwards relative. So they could still lean their trunk forward, but maybe their legs are still maybe biased, or they could be symmetric. So I think the trunk leaning forward, there's some maybe ties between extreme angles of human walking and maybe an ostrich or bird-like behavior based on where they put their trunk. So I know there's some studies that have looked into that with leg angle asymmetry, but I guess we didn't go too closely into it. But I think there would be some ties between extreme angles of trunk and the leg morphology of
Because
birds.
the center of mass is nice and high if the trunk is tall, but for the bird it's maybe forward or right around the hip. So you don't have the same kind of control authority to influence your speed or anything else.
Yeah. So whether or not that would influence their asymmetry to counter having that trunk forward, or maybe they've adopted because they have a very different morphology, they could be doing something else that may not be the same.
Allison?
Kind of similar to the last question, do you think if someone had a really heavy backpack that they were wearing in front of them and walking uphill, you would see the trunk lean, or do you think that might be this move the center of pressure forward for them?
Yeah, for sure. We talked about maybe trying to do studies where we would bias. We'd have some sort of backpack where it could bias the center of mass forward or backwards in a way that they would move the trunk, not what they would naturally do. So I think you can play with like where you put the center of mass, and then that would change the dynamics. So I think that would, it'd certainly be a part of it. We were to bias the mass that they were carrying.
Oh, Glenna?
Hi, thanks. I think this probably complements the muscle physiology question in that where in the trunk does the lean happen? Is it a pivot at the hip joints? Is it in the lumbar spine? And could that influence potentially more of the leg muscles or the thoracic muscles?
Yeah, that's a good question. Because here we simplified everything just looking at the markers and the angles between the pelvis and the trunk. So I think if we had like measurements of maybe muscle activity to see maybe where people were using more activation to control the trunk, I think that would be important to know if it comes more in the lumbar region or maybe more at the hip.
All right, let's thank Amy and move on.